Welcome back. This is part 2 of comparing different types of graphs. If you have not yet seen part 1 about displacement versus time graphs, you'll need to go there first. Now, today what we're going to do is we're now going to go into velocity versus time graphs. So we're going to talk about those. These are a little bit harder. Displacement versus time graphs are fairly easy to understand. So let's go look and compare a displacement versus time graph, and then we'll see how it changes by looking at a velocity versus time graph. So here, if we have a position versus time graph, we said our y-intercept position is where we're starting. So here we're saying we're starting at the start line, at the origin at 0, 0. We're moving up with a constant velocity of some number, and we can get that number by finding the slope. Then we stopped, didn't move. Then we're going to reverse until we come back to the origin, and then we're moving away, and again at a constant velocity. But here, we're going to change it. This time, we're changing it to a velocity versus time graph. Velocity is going to change a lot of what's happening here. And with that, it's going to change what we are talking about. So in a velocity versus time graph, we can have a very similar looking graph, but this time the y does not tell us where we are, but it's going to tell us how fast we are going at time equals 0. So again, this is time equals 0. This is telling us that we have a velocity of 0. But if we had a y-intercept of here, this tells us that we have some number. We are starting with a velocity of something, let's say 30. So we are starting with 30, while this one is starting at 0. We don't know where it's located at, but we know that it's starting with its y-intercept. So let's go back to our initial thing, and I'll click these so that we can look at them. Now here's our velocity. Our y-intercept is our initial velocity. So our y-intercept here is initial displacement. Our initial velocity, I bet you guys can guess what the acceleration is, but we'll get there later. So then the velocity is this initial. So now we got to talk about the slope. The slope is, again, let's look at this graph again. And we'll redraw. So let's put a nice graph. So we started at some number, let's say 25, and we're going up to a height, let's say 50. We started at time equals 0, and we're going to go to time equals, for easy math sakes, 50 seconds. So we're going 25 meters per second, then we're going to go up to 50 meters per second in 50 seconds total. So the slope is then rise over run. So again, slope is rise over run. The rise is my velocity. So it's my change in velocity. So I'm changing from 25 to 50 in a certain amount of time. Well, this looks familiar. This is acceleration. So my slope of a velocity is equal to acceleration. So here we have a positive slope, meaning we have a positive acceleration. Here we have a 0 slope. That means it has an acceleration of 0. Down here we have a negative slope. So let's go back and fill out the chart. Ooh, went too far. So the slope is the acceleration. If you have a positive slope, it means that you are accelerating in the positive direction, meaning your velocity is changing in the positive. If you have a negative slope, it's a negative acceleration, or you're changing your velocity. So if you want to write that down, then you're more than welcome to do that. You can write down that this is a positive acceleration, negative acceleration. And if you have a zero slope, it means that your acceleration is 0. So let's talk about that. What is that going to look like? What do those terms mean? What does a acceleration and a positive acceleration look like? A negative acceleration and an acceleration of 0. So we already said that the slopes are going to be positive for a velocity versus time graph. And a velocity versus time graphs, it will be a negative slope. And then we said if it's flat for this, again, for velocity versus time graphs. This represents that when we have an acceleration, that means we're speeding up. We're getting faster. So this is speeding up. Speeding up. We're gaining velocity. We're velocity of a lower, then we're going to become higher over a certain amount of time. Negative acceleration is slowing down. So we started up high, and now we're ending at a lower amount of speed in a certain amount of time. An acceleration means that we started at the same speed and we are still maintaining. Now there's two options. We could have it so that the slope is along the x-axis, above the x-axis, or below the x-axis, all still same slopes, but they mean different things. If it's on here, my velocity, if it's on the x-axis, that means my velocity is 0, meaning I am staying put, not moving. But if it's above, that means I have a positive velocity, and if it's below, I need to have a negative velocity of some number. Means I'm going to be moving in the positive direction. If it's above the x-axis and it's a flat line, means I'm moving at a constant speed, not changing my speed. If it's below, it means I'm moving in the negative direction, away from it, in reverse, away from the origin, in the negative direction, but not speeding up or slowing down, just moving away. So these are the three different scenarios where you have those three different options. Now, if you have a straight, that means if it's a straight line, it means you are accelerating. Now, if it's curved, meaning that in the velocity versus time graph, this is a curved line, this is going to represent a changing in acceleration. Now, we give that a term, and we call it a jerk. But in physics, we don't like jerks. In calculus, you'll learn about jerks. They're called the fourth derivative. For us in this class, we don't care about jerks. We're not going to do with it. So we will never see changing acceleration, meaning that we will never see a velocity versus time graph curve. Velocity versus time graphs will always have a positive, negative, or flat slope, always. Unlike position versus time graphs can have curves, and the curves represent acceleration. So in a position versus time graph, it will have curves, but in velocity versus time graphs, they do not. You'll never see it in this class unless you take higher level physics, where you can learn that math. All right, so again, we're never going to see that. Areas under the curve. area is going to represent the displacement. Now, what does that mean? Well, if I look at a velocity versus time graph, I look here, I'm looking at, let's say, this triangle from here. This is time equals 1, time equals 0, and here's my speeds. Well, my area is this part. In calculus, we call this an integral. But in regular physics, we just call it the area under the curve. If you were to calculate the area, which just happens to be a triangle, so that would be 1/2 base times height, and we were to calculate that, we would get its position, how far it went in a given amount of time. If you were to do that for this square here, you would get, again, now that's a square, so that's just base times height. That would still give you how far you went, its position, how far it went. So in a graph, you could actually look at this whole thing. Now, in calculus, we call that an integral. But you're not going to ever see that, so don't worry about it. Now we're moving into, what are the curves? Well, the curves have the same velocities. So we can look back here again, and we can say, what does the curve that looks like this and like that on a velocity versus time graph? So that means it has the same speeds. They have the same accelerations. They have the same changing speeds. They're just going to start at the higher. This one's starting at a higher speed. This one's is starting at a lower speed. But they're accelerating at the same rate. If they went flat, well, these would have the same amount of. They're going at a constant speed, so their accelerations. So their accelerations are going to have the same velocity. So if the curves coincide, the objects have the same velocity. How do we know if it stops? Well, this one's trickier because we said earlier that it stops in a position versus time graph when it went flat. But in a velocity versus time graph, it means it's when it crosses the x-axis, when its velocity is 0. So whenever it crosses that x-axis is when you are stopped. So very different. They look differently, but this one means it's stopped. This one means it's stopped. So that's kind of one of the tricky parts. They are different graphs. Then the last one is, how do we know if it has uniform acceleration? Well, uniform acceleration means it just has an acceleration, doesn't change its acceleration, doesn't have a jerk, which we don't deal with, and that means that it has a straight line, meaning it has a slope. It could be in positive slope or a negative slope, but if it has a 0 slope, it has no acceleration. All right. In our next video, we're going to talk about is acceleration versus time, and we will end this video with that. So make sure, if you need to, pause this video, record all the information down, and if you have any further questions, ask your teacher.